Hello friends, this video on Haloalkanes and Haloarenes part 26 is brought to you by examfear.com. No more fear from exam. So let's have a review of SN2, E1, E2 and SN1. So if you see the first one is my SN1 reaction. SN1 reaction, what we have told that this happens in the presence of protic solvent. Correct? Why protic solvent? Because protic solvent will favor the leaving group to leave and form a carbocation. So this is protic solvent and here we have carbocation formation, and it's good to have a tertiary group, right? Because that also favors tertiary group, and good leaving group is must here. So these are the critical thing for SN1 reaction. So it will be a slow process, but this is the most critical process where you form carbocation. So carbocation formation is required. For carbocation formation, tertiary group is better, and the solvent has to be protic because the protic solvent favors carbocation formation and the leaving of the leaving group, and the leaving group has to be good, right? This is my SN1 reaction where this is my substrate, generally tertiary. There's a leaving group leaves on its own, and it's a very slow process. And there is a nucleophile. Nucleophile can be weak. I don't care about nucleophiles, so I have not written the nucleophile here at all. And the nucleophile attacks, and there is no inversion. There is no inversion here. No inversion. Or actually, it is 50-50 mixture. We have discussed that. So let's ignore that part, not to make it more complex. That is only for the optically active compound. So these are the critical thing for SN1 reaction. It has to be protic solvent, tertiary group, good leaving group, and carbocation. Let's see E1 now. So E1 also is similar to SN1. There also, if you see, it needs a good protic solvent because it has to, the leaving group has to leave. So it needs protic solvent, and tertiary group is better here also. Correct? Good leaving group is also required here. And the base here, it will be, there will be a base. A weak base is also okay, weak or good base. That is mandatory here, right? Because without base, the deprotonation won't happen. So if you see this step and this step is same in both reaction, but here instead of nucleophile getting attacked, so here if you see nucleophile is required actually, but here if you see the nucleophile is required, right? Nucleophile is required, at least there has to be a nucleophile. Whether weak or strong doesn't matter because already plus, so even a weak nucleophile can attack. Here base is required, right? So here base is required, here nucleophile is required, right? This is base and this is nucleophile. These are this is the main difference, right? So here instead of nucleophile we have base. So what base will do? Base will attack this hydrogen and take out this hydrogen from it and form a double bond. Correct? So if you see both the reaction, the first step is still here, it is all same, but here in this case there is a nucleophile that attacks because there is a carbon with a positive charge. It is a little unstable, it has to be stable. There are two options. One is you add something with a negative charge, or second is you remove something with a positive charge, right? So if you have a positive charge, there are two options. One is you remove something with a positive charge, that is in this case you are removing H plus ion, or you add something with a negative charge, that is in this case you are adding a nucleophile, right? So that is a main difference, but in both the cases you need protic solvent. Please pay a little more attention in this slide because this explains all these four kind of reactions very clearly, right? So both these reactions need a protic solvent. I'll just put a mark here because both are almost similar. The only difference here is here you need a nucleophile to with a negative charge to compensate for the positive charge, but here you need a base that can take out one H plus, right? So here you compensate, you add a negative charge nucleophile. Here you remove H plus, and to remove H plus you need base, right? To add a negative charge you need a nucleophile. So that's the difference. If you have a nucleophile will attack this carbon and form a bond. It will become a substitution reaction, SN1 reaction. If there's a base will take out this hydrogen from here and it will form a double bond. It will become a elimination reaction. So if you see, as I told, base and nucleophiles, there will be sometime we have a base, for example OH minus. This may act as nucleophile and may act as base also, for example OH minus, right? So there are some scenarios where we'll see that both the reaction happen. That's why we'll say that E1 and SN1 are in competition. We'll take some examples where we see this compound which we have behaves like a nucleophile and form a substitution reaction, and sometimes this compound behaves like a base and take out the proton. The next is the SN2 reaction and E2 reaction. So as I told, in the first two reactions, it was the leaving group that was deciding the reaction, right? It was the leaving group that was the hero here, right? The leaving group was the hero, and that's why it is SN1 or E1 reaction, because these are the heroes here, right? The leaving groups were the hero. But in this case, the leaving group is not the hero. The nucleophile or the base is hero, correct? So in this case, if I'm talking about SN2 reaction, my nucleophile has to be strong, right? So my nucleophile has to be strong for SN2. If I want to make my nucleophile all the more stronger, I will need a protic solvent, because if it is a protic solvent, the protic solvent itself will react with nucleophile and make the nucleophile weak, right? So I'll go for a protic solvent, correct? Now since in this SN2 reaction, the nucleophile has to attack carbon, it is good that steric hindrance is not there, right? No steric hindrance. That means I am looking for 1 degree or 2 degree CX bond, correct? And in this case, good leaving group is required in all, actually in all good leaving group is required, but in these two it is mandatory to have good leaving group, because the good leaving group is the one which decides the reaction. In this case, even the leaving group is not good and the nucleophile is very strong, nucleophile can kick this leaving group out, even if this leaving group is not a good leaving group. If the halogen is not a good leaving group, if the nucleophile is strong, it can kick this nucleophile, the leaving group out. But in this case, the reaction depends only on the mercy of this leaving group. The leaving group has to be strong. If the leaving groups are not strong, the reaction won't happen, correct? So for SN2, the nucleophile is the hero. The nucleophile is the hero. It has to be strong, and to make it all the more strong, we make sure the solution is aprotic, so that the nucleophile is very strong. As we've explained that the strength of the nucleophile depends on the solvent, right? For example, I- and F-, the behavior change based on the protic and aprotic solvent. We have discussed in the past few slides. So here we'll try to make the solution aprotic so that the nucleophile is very, very strong, because these are my heroes. So in this SN2 reaction, the strong nucleophile is mandatory, aprotic solvent, no steric hindrance, and it has to be a first degree or second degree carbon. So the reaction is like that. If a nucleophile attacks from the back and this leaving group leaves, one step process. One step, but here both the substrate and the reagent determine the reaction, so it is SN2. Now we'll talk about the E2 reaction. Here, instead of nucleophile, I have a strong base. I have a strong base that is required. Strong base is required, right? To make the strong base all the more strong base, we use aprotic solvent, because if we use protic solvent, my H plus will react with my base and it will make the base weaker, right? It will be acid-base reaction. So I don't want to happen that. So if I don't want that to happen, an acid-base reaction that can make my base weaker, I'll make sure the solution is aprotic. Also, it is good that it is 1 degree or 2 degree, because this is not much critical here, because even if there is a steric hindrance, the base can attack. But it is good that it is a less degree, right? So in this case, the base attacks this hydrogen of this carbon. So the other carbon makes sure that the halogen leaves from the other carbon. So it is a double bond form. We have discussed this reaction mechanism earlier also. So to repeat, let's have this slide. In SN2 reaction, steric hindrance should not be there, because the nucleophile attacks. Since the nucleophile has to attack, the nucleophile has to be strong. To make the nucleophile all the more strong, we use aprotic solvent. For E2 also, the steric hindrance should not be there. It is good, it is not there. The base has to be strong, because it is the base who is the hero. The base is the hero here, the nucleophile is the hero. To make the hero a better hero, we make sure the solvent is aprotic. For SN1, it is all depend on the mercy of the leaving group. So the good leaving group is must. This is must here, right? Good leaving group is must. Steric hindrance is okay. Actually, it is better, because with that it helps in leaving group. So for a good leaving group to leave early, we make sure the solvent is protic. That is what we make sure, right? Because here the leaving group is the hero, right? The good leaving group should leave, and we make the protic solvent to be protic. And the nucleophile can be weak also, because once it's a protic solvent, any base can attack here. Sorry, is SN2. So any nucleophile can attack. So nucleophile is okay. In this case, steric hindrance should not be there. Here also the leaving group has to be grouped. This is the one that is a critical factor. As I told, to make it all the more better leaving group, we make sure the solvent is protic, right? Because the protic solvent helps the leaving group to leave early. The base can be anything. Please note, here I had a nucleophile, here I have a base, because the base is the one which will attack on hydrogen. The nucleophile will attack on carbon. This will attack on hydrogen, right? To make sure we form a double bond. So if you see, one note I have, if I have a strong nucleophile but weak base, for example NaCl, this will favor SN2 over E2. But if I have weak nucleophile and strong base like phosphogen, it will favor even over SN1. We will take these examples later, where we will talk about some of the scenarios where we will try to find whether it is E1 SN1 or E2 or SN2. So there will see this, where we will say that if it is a strong nucleophile, right? The nucleophile is strong, but the base is weak base. As I told, the same compound work as nucleophile and the same compound work as base. Correct? As I told that, the same guy. Now, and if I'm assuming that I'm having a tough time between selection of SN2 or E2, because if it is a aprotic solvent, let's suppose this is happening in an aprotic solvent. So I can clearly eliminate SN1 and E1, right? Because this is a protic solvent. This is a aprotic solvent, it is SN2 or E2. Now I have to decide it will be a SN2 or E2. As I told, in SN2, the nucleophile is the one which has to be strong. And for E2, the base has to be strong. But if I have something which is a weak base, but strong nucleophile, that means it is SN2. Correct? So those kind of things we'll see that. First step we'll do it, we'll eliminate whether it is a E1, E2 or SN1 and SN2 based on the solvent. We'll see some examples on that. Let's see these examples where we have to predict whether the reaction is SN1, SN2, E1 or E2. Let's take this reaction first. So I have this compound, let's suppose, and I am having this DMF, and I have CH3ONA. So we have to find whether it is a even reaction, E2, SN1, SN2. First, try to understand DMF is what? DMF is aprotic. Correct? So DMF is aprotic, that means E1 and SN1 is ruled out. As I told, for E1 and SN1 reaction to happen, the hero is 1. Who is the hero? The leaving group. And if the leaving group is hero, you want to make it a better hero, you make sure the solvent is protic, because protic solvent makes sure that the leaving group leaves early. But if it is an aprotic solvent, that means SN1 even is gone. That is not the option. Now we have the option of SN2 and E2 reaction. So we'll see if it is a strong base, it will be and strong nucleophile. So if it is a strong nucleophile, right? So nucleophile we talk about SN2 reaction. It's a strong base, we talk about elimination reaction, so it will be E2. That's what we will see, right? So if this guy is a strong base, it will be E2 reaction. If this guy is CH3O minus is a strong nucleophile, it will be a SN2 reaction. But we know that CH3O minus is strong nucleophile. We know that. It is also a strong base. Correct? Since this CH3O minus is both strong nucleophile and strong base, that means it has to be both SN2 or E2. There is a probability, not sure. I mean, both are possible now. We can't eliminate now. But for elimination reaction to happen, there is one more requirement. That requirement is the beta carbon should exist. It's not very critical requirement, because we can have a reaction where both halogen and hydrogen leaves on the same carbon. So let's ignore this actually, because let's ignore this. Let's ignore this because there can be a scenario. So this is SN2 or E2. Both are possible with this. But actually in this case beta carbon is there. This is my alpha carbon. So I have a beta carbon here, I have a beta carbon here. There are two beta carbons. So that is true in this case, but I don't think that is a very critical scenario because we have seen a alpha dehydrohalogenation also. So let's suppose this is my case. So with this we conclude that both SN2 and E2 is possible. Let's see other factors which favor SN2. For SN2 we have seen that it is good that it is 2 degree or 3 degree, right? Oh sorry, 1 degree or 2 degree at the max. So in this you see this is 2 degree. That means it is fine, right? Both favors SN2 or E2. So let's see what the product will be if we go for SN2 reaction. So this is my compound. This is H. So I'm going for SN2 reaction. That means I'm talking about strong nucleophile. So this is my nucleophile now. This is my nucleophile. So nucleophile attacks what? Attacks carbon. This carbon. Correct? So with this, what you will get is this nucleophile will attack this carbon and it will form this guy. Correct? Because OH3 minus will attack this carbon and this bromine will be kicked out and OCSA minus will take this place. Let's talk about E2 reaction, how it will happen. Same guy. Here we have Br and here we have H, all single bonds. Now this is CH3O minus. As I told, this is E2, this will act as a base. Correct? The same guy is acting in the nucleophile. Now since this guy will act as a base, it will act hydrogen, beta hydrogen, either this or this. I took this. I can take this also, you will get the same product. This will attack this hydrogen and this will form a slightly negative charge, and then this Br minus will be kicked out. This guy will get a positive charge, this will get a negative charge, positive negative charge will form a bond. So what you will get is this, all in one step. So this will be my E2 reaction and this will be my SN2. So if you see in this case, the output will be both actually. For this reaction, the output will be both this product and this product, because both the reaction will happen here, SN2 and E2 reaction. Let's take another example, similar example, the same reactant I am taking here, but instead of my CH3O minus, what I am taking is, I am taking a complex reactant, this one, or you can say this is Na, and I am using, let's suppose, same thing, DMF here. This is my A protein. So since it is a DMF, that is A protein, I can easily rule out the possibility of SN1 and E1 reaction. Now this guy, my reagent is what? This is a strong base. What about the nucleophile? It is a bulky nucleophile. It's a bulky nucleophile. Since it's a bulky nucleophile, so see, strong base is required for what? E2 reaction. Bulky nucleophile is required for SN2 reaction. Just understand this. SN2 means what? Substitution nucleophilic. That means it needs nucleophile. Just understand, this has the word nucleophile, that means it is nucleophile, and this is not having the word nucleophile, that means it needs base. So SN2 needs nucleophile, SN2 needs the compound, the reagent to behave as a strong nucleophile, and E2 needs the compound to behave as a strong base. But this compound can behave as a strong base but cannot behave as a strong nucleophile. That means SN2 is not possible. That means it will go for E2 reaction only. Hope you understand. See, we had 4 possibilities. SN1 even we ruled out because this is A protein. A protein rules out SN1 and E1. We have discussed this because SN1, E1 depends totally on the leaving group, and to make the leaving group hero we need protein solvent. This is totally ruled out. right? Now we have the option of E2 and SN2. For SN2, we need strong nucleophile, that is the compound. The reagent has to be a strong nucleophile. For E2, the reagent has to be a strong base. But this particular reagent is a strong base but a bulky nucleophile. So it will not go for SN2 reaction. It will go for E2 reaction. That means the product will be something like this. This will be my product. This is a single bond. So let me draw it clearly. This will be the product. Correct. Let's take some more examples now. So, let's take this guy. Diisopropyl ethylamine. Right? So this guy is a good base and this reacts with, let's suppose, this compound, right? Steric hindrance here. This is a bulky nucleophile and this is a good base, and this whole thing is happening in a DMF environment. It is aprotic solvent, right? Aprotic solvent. So now see, since the solvent is aprotic, we can easily rule out SN1 even. Now E2 needs what? E2 needs base, good base. SN2 needs what? Good nucleophile. But this is a bulky nucleophile, so I can rule out SN2. So it will be a E2 reaction. So it will be a E2 reaction. Correct? It will be elimination reaction. Somewhere it will be something like this. Sorry. It will be carbon here, it will be a double bond here, this will be the output. Some elimination will happen by one of the beta carbon. These are 3 beta carbons here. This is alpha carbon, there are 3 beta carbons. Correct. Let's take this reaction. I have this compound and I have NaC in here. And let me use again aprotic solvent DMF. So this is again, since it is a aprotic solvent, I can rule out SN1 even. Now let's talk about Cn minus. Cn minus is what? Is a weak base. We have seen Cn minus, Cl minus, I minus, the weak base, and it is a good nucleophile. Why good nucleophile? There's a charge, negative charge. So this needs good nucleophile. This needs good base. But is this guy good base? No, it's a weak base. E2 is not possible. So good nucleophile, yes. So SN2 is possible. That means this reaction will go for SN2 reaction, where this Br will be replaced with Cn minus and the product will you get is, this is the output. Correct. So this was a weak base good nucleophile, so it favored SN2 reaction. We'll take 2 more numericals in this case. So we have, let's suppose, this compound, this CH3, this is OH, right? And let's have temperature here. Now H2SO4 is what? H2SO, and this is heat, we are heating it. H2SO4 is what? Is a protic solvent. And please note, in this case, my reagent is also H2SO4, right? So reagent is also H2SO4 and solvent is also H2SO4. Correct. Now, since it is a protic solvent, my SN2 and E2 is gone, right? So we can discard SN2 and E2 reaction. So I have the possibility of SN1 and E1 reaction. But we know that SN1 happens at lower temperature and elimination happens at high temperature. This is something, please note this rule. At the lower temperature we have substitution, and higher temperature we have elimination. Since we are giving a temperature, so substitution is discarded, we have elimination. So it will go for a elimination reaction. So it will be something like this. This will be the output. correct? Instead of OH, you can also go for a halogen also. Let's take one more example here. So I have this compound with a thiol here with Br here. I have CH3OH here. This is my solvent and this is my reagent also. So my CH3OH is protic or aprotic? CH3OH is a protic solvent. Since it is protic solvent, that means I have to ignore E2 and SN2. This rules out SN2 or E2. Now I have the choice between SN1 and E1, right? But since there is no heat here, no heat means low temperature. Low temperature means what? Substitution reaction. So this will be failure and this will not happen. So there will be a substitution reaction. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.